So let's look at this one. Again, we talked about, this is our radioactive substance, and we came up with our function of y equals 100 times 1/2 to the x power, where x was our number of half-lives and y again was our amount of substance left after that time. And so if we're thinking about this question, right, so how long will it take for the substance to weigh 1 gram? Well, that's where we're going to put 1 in, right? 1 is our amount of substance, and that's going to equal our function, 100 times 1/2 to the x. So as before, we're going to try to isolate the variable, right? Solve it algebraically exactly like you know how. Divide both sides by 100. But now we have 1/2 to that x power. So this is that new idea of, okay, this is where the logarithm comes in. Let me see, so I'm going to write 1 over 100 equals 1/2 to the x. But just as before, right, I want to undo this exponent here. So I'm going to take the log, and my base is this same base, right? The same base as the exponent. So, and maybe I'm going to write it as a decimal just for, just for the way it looks. And I'm going to write that as log base 1/2 of this. And then I'll also write the 1 over 100, 1/100th as a decimal. So then what we see is that we have log base 1/2 of 1/100th equals, and just as before, oops, not orange, red, right? The x, this is our log properties. The x comes down in front. And so we have x times the log base 1/2 of 1/2, right? And that is exactly what you want, because what we want is for this whole thing, log base of 1/2 of 1/2, base 0.5 of 0.5 is 1. So that's why we want that whole thing to just, what it looks like it disappears. It looks like it cancels out. What's actually doing is it equals 1, and x times 1 is itself is x. So that's why that's how we isolate the variable. So that way this whole thing just equals x. Our log base 1/2 of now 100th. And so again, we can use our calculator. We're going to need the change of base formula. And I'm just going to use the natural log because it's less characters to write. So we'll have the natural log of 1/100th all divided by the natural log of 1/2, and that's going to equal x, or we can put it in Desmos. And we'll do both, right? We can put this in the calculator and we'll get, that's about, and we'll put it in Desmos and see how we read the graph again. All right, so here we are with our calculator. We can do our change of base formula. And see, so if you start with the, as it's written is the natural log of the number in the calculator, you have to put in the number first. So we have 100th natural log divided by 0.5, right? Half natural log, and it equals about 6 64/100ths of a year. So not quite 7 years, or a little bit more than 6.5 years. And we found that, when we were counting out the half-lives, or sorry, that's number of half-lives, not years, right? We said it would be about 35 years for it to be less than a gram when we were counting them out 5, 10, 15, 20 in our example. So now let's have a look at Desmos. So here's where we left off at Desmos, and right, I'd encourage you to try to write this equation and see, okay, what do we need to find, just like we did with this one. It's not as big of a number, so you can read it right from the graph. So I'm going to turn off these ones and I'll move them out of the way. So this is our function that we were seeing. Oh, my sharing is the wrong share. Sorry about that. I was talking over the Desmo screen. Here we go. Here's our Desmo screen. All right, so we left off here with our log base 2 of x. Now we have our function log base half of x. And we'll turn this on and see what it looks like. Ooh, it looks pretty different. So here, let's remind ourselves when we had y equals 100 times 1/2 to the x, right? Our x was the number of half-lives and our y was our amount. Now, when we're talking about our logarithms though, our x, and I'll change these colors so that way, let's make this red. We don't confuse them. All right, our x now is the amount and our y is going to be the number of half-lives because we're dealing with the log function. So I guess maybe before we go there, we'll put this in as y equals 100 times 1/2 to the x power. And I'll put this in blue since I wrote in blue here. All right, so what this is saying is we want to know, right, when is y, when is our amount exactly 1? And so we can read that from the graph. We can read this right from the graph here. So we want our, oh, I passed it. Right here we see at 6.6 half-lives, we're at 1.1 gram, right? That's our amount. We're at 6.6, we're at 1.03. And we don't have exactly, right? It's hard to get the y value to be exactly 1, but we can kind of read that from there. So you can solve any of these with either rendition because they're the exact same, modeling the same exact idea, just the x and y's are switched. So if we think about now the log function, and now that looks really kind of crazy looking, but what we want to see is our x is our amount. So we want to find when and it's not necessarily the amount that we have, like we want, like here, if we were thinking, we want to find not when x is 1 for the amount of grams, but because it was the 100 in front, which I guess maybe we need to incorporate that. Maybe that's, if we want the x to be strictly the grams, so we started off with the 100, it would have been x divided by 100. And so now we can see, I think, right there at 1 is our y. Can I move this up a little? Sorry, my annotations are now. Right here, now when x is 1, our y is the number of half-lives, that's 6.644. So that, and I can't do both. Here, maybe we can hold this, right? This number right here is saying, right, my x is my 1 gram, my amount, and here my y is the number of half-lives, which is about 6 6/10, or if you want 6.64, either way you want to write it. That's what this point is telling us right here. And every time I take my finger off the cursor, it disappears. So that's how we can read this graph. If we were thinking about, just like how we saw it from here, with this, the 100 in the here became the 100 here. That's why that changed. And when we saw that this, when this got to be, right, with this one, the blue one, right, our X is the number of half-lives. And so we're looking at what's our X when our Y is about 1. And we can't get exactly at 1. We're pretty close here, right? Either just over or just below. A little bit closer, right? And so you can think about, if it's all 6 6/10 or whatever, close enough. Or just like how we did last time, if you don't like the change of base formula or don't remember it, you can just type it in as the log base 0.5 or 0.5 of, and we had, right, 0.01. And look, again, it tells us that exact number right here. So this was saying, that's a weird number. I don't know why that's, I don't know what's going on there. Sorry. So any way you'd like to do it, whether it's reading it from the exponential equation, that's fine. From the logarithmic equation, that also works, or just typing in the log, so that way it does the calculations for you, also works. So you can get to this, this purple point algebraically, and then you can, sorry. There we go. I was trying to remember what point it was looking for. You can get to this point algebraically and then just type it in Desmos. Or you can read it from the graph if you like the red one of our logarithmic function, and then you can see that my X is my 1 gram, my amount, and then my Y is going to be those number of half-lives, the question we were looking for, right? How long does it take to get there?